So welcome to session 2 of the first day of the FDP. So I hope you are able to see my screen. Okay, great. So this session, I will take this session and then the next session will begin at 2:30. So we have to cut down the lunch break today because the inaugural session stretched a little bit more. But tomorrow onwards, we will stick to the schedule. Okay, so let me start with the presentation. So I'm going to talk to you about again introduction to IoT, scope and challenges, but unlike the first talk, this will be more focused. The first talk in the first session was an overview. It covered many different topics, many different aspects of IoT. In my talk, I'll focus on some well-defined aspects of the Internet of Things. Okay, so the outline of this talk is we'll give a small background on IoT, then what are IoT devices, what is the IoT architecture. Remember that this FDP is focused on system and architecture and system level design of IoT, and that is how most of the sessions are planned. So that I will talk about. Then I will talk about IoT protocols, basic introduction to protocols, because you will have later on sections focusing on the protocols. Scope of IoT, I will give you one, I will show you one video of smart farming. Then what are the challenges in IoT? And then I will specifically talk about machine learning in IoT as a specific challenge discussion, and then we'll conclude. So what is IoT? So IoT stands for Internet of Things. And you can compare and contrast this with the usual concept of internet, which is exchange of information. So in the normal case of internet, we exchange information since human beings are the users of the internet. When we talk of Internet of Things, we are talking about things or physical objects which talk to other physical objects and perform some action. Okay, but they make use of the same internet, but it is the things that interact with each other. So that is why this is called as Internet of Things. The objects, these physical objects, can have sensors and or actuator and software. And sensing and actuation happens over the internet. So internet provides the backbone over which the IoT sensors act, and then the actuation using actuators happen. Okay. So one can ask, what was the first internet connected appliance? Okay, because we're talking about things in Internet of Things. So what was the first what was the first, and we'll take questions at the end because that will be better. Okay, so the first internet connected appliance was a Coke machine, a Coca-Cola vending machine, that was connected to the internet in 1982 at the computer science department of Carnegie Mellon University. Okay. It was built by these people, and Mike Kazar, David Nichols, John Sarney, Ivo Darham, and you had this, the work was distributed like this. So one person worked on server software, the other one worked on documentation and user software, the third person worked on hardware, and the fourth person worked on finger interface. Essentially, how this all came to happen about is that these people used to work in computer science department, and then there was a Coke machine which was lying in the corridor or somewhere in the hallway. Now it was a pain to get up from your seat every time you needed to get a Coke bottle and walk to the machine. And then when you go there, you find that there is no Coke there. There's no bottle. Everything has been consumed. And then you have to inform the company, and then it would come and fill up. So they thought that it would be better if while sitting at their work desk, they could see and identify whether there is sufficient Coke stock in the vending machine or not. So it was this aspect of the connected Coke machine that was created, and everybody on their computer terminal, they could see whether there is a bottle available there or not. And if it is not there, Coke company, the vendor, could be informed and they would come and fill up, and then they could see the status again that yes, now the vending machine has the Coke bottle, so they can go and collect the Coke. So the architecture of Internet of Things has a very basic concept. So this is a very high level concept where you have IoT device 1, which could be a sensor, which will send some data. And then you have IoT device 2, which is the actuator or the receiver, which will act on the data received, or the data could be stored somewhere, like in a cloud server. Okay. So IoT device 1 talks to IoT device 2 through a communication infrastructure, which involves gateways, internet gateways, routers, etc. And this whole communication infrastructure can be thought of as your local area network, LAN, wide area network WAN, or the internet, depending on what is the geographical scope of the connected devices. So in the case of the CS Carnegie Mellon University's Computer Science Department Coke machine, initially it was a local area network, and then later on, now it is connected to internet. Okay. So this is the very basic architecture. If you can understand this architecture, then the rest is all about details, getting into the details of the communication infrastructure, details of IoT devices. And cloud server is again about storing the data and how you can talk to maybe IoT device through a cloud server. So this can also be part of the communication infrastructure. Here I am showing it as a storage platform. So let's now talk about IoT devices. So what are IoT devices? When we talk of Internet of Things or IoT devices in IoT, we mainly refer to edge devices. Specifically in this presentation, I'm focusing on edge devices. So I'm not going to talk about gateways and routers. I'm going to talk about IoT device. And that is also the generally accepted connotation or meaning of IoT devices, that they refer to the edge devices. Now, these are devices with much less computational capability than a graphics processing unit or a high-end CPU. Okay. So unlike your processor on your laptop or desktop or the GPUs there, IoT devices have much less computational capability. Here is an example of an IoT device. This is Amazon Dash button for Somat dishwater tablet. So Amazon had started manufacturing these Dash buttons, which you could keep in the house anywhere. And for every product, they had a button. And if say your house is going to fall short of those, the stock of that particular product, you could just press this button and it would connect to Amazon servers, and Amazon would ship the item for which this button is designed to your home. Okay. So there were buttons for Tide detergent, there were buttons for beverages, and so many other things. So it manufactured millions of these buttons and sold millions of these buttons to its customers. And you can think it's so easy, like if say you are running short of apple, all you have to do is press a button and then Amazon will deliver the apple to your house. When you open the case of this button and look inside, this is how the architecture, this is how it looks like. It has an ATAL processor and some a little bit of memory and things like that. That's all, nothing else. So compared to your laptop or desktop, you see this is a very tiny device with a very small processor or microcontroller, very little memory. So its computational capabilities are much less. Another example of an IoT device is Amazon Echo Dot, which some of you might be having or you might be familiar with. So Echo Dot allows you to connect to Amazon through the Alexa app, and you can play songs, you can order food, you can make calls to people, you can send SMS to your contacts, all of that you can do. When you remove the casing of this device, this is how it looks like inside. Okay. It's just a small motherboard or a small PCB board that has some components. What are those components? So it has an ARM processor, which is ARM Cortex A8. So ARM is the most prominent low power processor design company. Okay, now it has been bought by NVIDIA, but all your smartphones have ARM processors in them. Okay. ARM stands for, in the name itself, A for architecture, sorry, A for application, R for real time, and M for microcontroller. So these are the three different kinds of microprocessors that ARM was designing. Now the ARM processor that is there on this digital media platform, this red box, this chip, this is a digital media processor chip from Texas Instruments. So the ARM processor that it has a maximum operating frequency of 800 megahertz or 1000 megahertz. Compare this with your i7, i8, i9, these processors. They are running into gigahertz, more than 3 gigahertz, more than 2.5 gigahertz. Whereas here it is only 800 megahertz or 1 gigahertz, much less. It also has a DSP processor from Texas Instruments, C64X, one of that. And then it has on-chip L2 cache and RAM. So this is the memory on the chip itself, which is only 256 kilobyte. Okay. Compare this with the L2 memory in your laptop or desktop, which runs into megabytes. These days it runs into gigabytes also. Your DRAM the DDR on your laptop will be a few gigabytes. The on-chip RAM or on-chip L2 cache in Intel processors would be a few megabytes, 4 megabytes, 8 megabytes, like that. Okay. Compared to that, 256 kilobytes is a very tiny amount of on-chip memory. Okay. And then this, of course, this platform, this Amazon Echo Dot had these ports, USB, SPI, I2C, and UART, 4 of each. Okay. So overall, when you look at this table, you can understand that this device has much less computational capability. Okay. And all that voice recognition that you see in speech recognition that you see in Amazon Echo Dot, that is actually done on the cloud, on the server, not on the device. Okay. Because your device has limited computational capability, and speech recognition and those kind of tasks, they need more computational capability. Okay, so with that introduction to IoT devices and a very basic introduction to IoT architecture, let's get into a little bit more of detail of IoT architecture. So this architecture that you see at this diagram is very complex. Okay, and what Professor Subudhi mentioned in his talk, this is sort of a summary of that. Okay, this diagram is actually from IBM's IoT business group. Okay, you can see the name here, IBM platform. It has a lot of elements. Some of the things that I want to highlight to you are things like user applications here. Okay, let me switch to pointers. So user applications here. Okay, then you have sensor gateway here, and then you have application runtime here, and then you have user management and device management here. You have some analytics and blockchain integration here, and here is some connectivity with enterprise network. Okay, so these are some major blocks in this diagram. Now these things, user management, device management, these are also essential aspects of IoT. Why? Let me give you an example. If you have a house, in your house, if you have a smart meter, okay, that measures how much electricity you are consuming, when you are not consuming, etc., then that smart meter should not be tampered with. Okay, so the smart meter will be given to you by your electricity company, and they will have the ability to configure the user. So that meter should be registered in your name, it should be configured in your name, as well as protect the smart meter from any tampering. Okay, and they can also do remote management of the data and content on the smart meter. Okay, so smart meters, electric meters is a very common example of IoT. Then this can also be integrated with blockchain, etc., and do some analytics at the background. So all the data that is collected from, say, thousands of users of a utility company, say like an electricity company, one could analyze all of that data to see how the customers are using electricity, when the demand is high, when the demand is low, in which regions of the city the demand is higher, in which regions it is lower. All of that can be done through analytics. And of course, you can add artificial intelligence and machine learning to this analytics as well. And this information can go to the enterprise data of the company. Okay, so the company will maintain some data related to business which is not exposed to other users. So all this analysis can become part of the business related data. And the sensor gateway here on the left is essentially sensors that are available on user homes, like the electricity meter, smart meter. It has to send the data through a gateway. So this is that gateway that sends the data to the company. You can see that this gateway is connected to edge devices. So this is your smart meter. Okay. So don't get too concerned about the left and the right and the top and the bottom arrows, but this is the main idea behind using an IoT platform, small devices like edge devices, connecting them to network through sensor gateways, managing these devices through user management, device management roles, collecting the data through the use of these devices, doing some analysis on it, and preparing business cases. So this is how technical aspects and business aspects of IoT are combined in this diagram. Another example of sensing in IoT is this, where this person here is touching a sensor. Okay, it senses the touch, passes on to a microcontroller unit, which uses a wireless connector or a wireless antenna to transmit the signal to another wireless antenna, which acts as a receiver. It takes these signals, passes to a robotic control circuit, and then this robot does something. And it passes, whatever it does, it passes that information to this receiver here, and this receiver is connected to a display here. Okay, so this is like some sort of a surveillance system where somebody is touching, say, some sensitive part in a building. That information is passed to a microcontroller. It conveys that information through wireless communication protocol through a robot. That robot then moves around and maybe captures some video or audio or something like that. And then that robot passes that information to this receiver, which is connected to a person's laptop or desktop machine, where that person can see what is happening in real time. If that person wishes to send that data to some other person sitting in some other country or in some other city, he can use the internet also to move this data over the internet. Okay, so this is another example of sensing in IoT. Now we have an example of actuation in IoT. So this is a smart bulb. This is from Sylvania, Osam, Sylvania. Okay, this smart bulb can be configured, can be turned on and off using your phone. Okay, so if you look at the guide, what they call as the onboarding guide or the user guide, these are the three main steps listed here. Okay, so you have your smartphone, you connect to the Wi-Fi at your home using your smartphone. Okay, then you download this app called Lightify on your phone. Okay, and then this is the Lightify gateway. It is a hardware device that you need to plug into a power socket in your home. Okay, and then the app on your phone and this gateway get connected, and one of these gateways can help you control 50 smart bulbs. Okay, so now if you do an action on your phone, on the app in your phone, that action on and off will be captured by the gateway, and it will be captured by the gateway and will be routed to the bulb. So the bulb will be switched on or off. Okay, so this is an example of a connected home where, you know, by sensing what the user is intending, so sensing your on and off action on the phone in the app, you are able to turn on or off the light bulb. Okay, so this is one good example of actuation in IoT, and it's a very simple example, nothing complex. Now you see here that your phone talks to this device, this IoT gateway, over the wireless connection or some protocol connection. This wireless gateway will talk to the light bulbs using some protocol. So in the IoT, we have in the IoT domain, we have various kinds of protocols. Okay, I will touch upon some simple protocols just to give you an idea. So one protocol is Constrained Application Protocol, or COAP, which is used for constrained IoT devices which join through a constrained network. So constrained IoT devices are essentially IoT devices with very less compute capability, and constrained network means a network that has low bandwidth, not very high bandwidth. So bandwidth in the range of a few kilobits. So nodes, so here is an example of constrained devices. Nodes often have 8-bit microcontrollers with small amounts of RAM and ROM. Constrained networks like IPv6 over low power wireless area network. You don't have to get into the details of this, but all you have to understand is that there is a constrained network where the packet error rates are higher and typical throughputs are of only 10 kilobit per second. Okay, this protocol is mainly for machine-to-machine applications like building automation. Okay, so in the IoT, you can have machine-to-machine, you can have man-to-machine, those kind of interfaces. This protocol is essentially for machine-to-machine, where one machine controls another machine. So the COAP protocol makes use of representational state transfer, which those of you who are familiar with web services design, you would understand this concept, and thus it provides interoperability between devices. You can see here that these are the COAP devices here, and this is an HTTP client here, and these COAP devices can interact with each other through the COAP protocol. They can talk to an HTTP client, which is not a COAP device, through a proxy that connects it to a HTTP server. Okay, the COAP devices can also talk to a server that has COAP functionality enabled in it. So you can see that there are different kinds of devices here. This is HTTP device, this is HTTP server, this is a COAP server, and these are COAP devices. So because representational state transfer is implemented in this protocol, these heterogeneous devices can talk to each other. Otherwise, it will be very difficult to keep them all connected. Okay, so the COAP protocol implements this representational state transfer. If you are interested in learning more about COAP, you can take a look at these links, but this is the basic idea. Then the next protocol is Message Queuing Telemetry Transport Protocol, or MQTT, which is essentially a very lightweight publish-subscribe messaging transport mechanism, which is ideal for connecting remote devices with a small code footprint and minimal network bandwidth. So small code footprint means that those devices, they have very small memory, on-chip memory or on-device memory, and the network connectivity between these remote devices is also weak. This MQTT protocol makes use of what is called as MQTT broker, which is a server that receives messages from clients, and then there are MQTT clients, which is basically any device which can be a simple microcontroller up to a full-fledged server that runs an MQTT library and connects to an MQTT broker. I will show you a diagram next. What I can tell you at this point in time is that MQTT protocol is used by one of the cab hailing services in Germany. So in India, we have Ola and Uber. In Germany, I don't remember the name of the automobile company, but there is an automobile company that uses MQTT protocol for offering its cab services. So here is a very simple implementation example of MQTT protocol. Okay, so here is a sensor, a temperature sensor. Here is the MQTT broker, and these are the subscribers, mobile phone and maybe a cloud account. Okay, so both the mobile phone and the cloud account, they subscribe to MQTT broker, telling it that they want to subscribe to a topic, say temperature. Okay, this sensor here is the publisher on topic temperature. Okay, so whenever this sensor senses a new temperature, it publishes that value, sends it to the MQTT broker, and then the MQTT broker looks up a directory, so to speak, of all those devices on or cloud accounts which have subscribed to the topic, and then it sends or publishes that value to them. So this is a very simple mechanism of publish and subscribe. Okay, so this is the publisher here and this is subscriber. They connect through the MQTT broker. Okay, this is like very similar from your real life examples. If you're in a big city and you're looking for a house, sometimes to rent, sometimes you may make use of a broker. Okay, and the broker has information about houses from the owners of those houses, and here are the clients. So you tell the broker that I need a house, so that's the subscription. Any person who has a house to rent, he tells the broker that I have a house to rent. The broker passes on that information to you, and that is how you get to know that there is a house in so and so locality to be rented. So that is a real life analogy of MQTT. Okay. Now this is a list of IoT protocols. This list is quite big. This is roughly 16 protocols shown here. There's Bluetooth, Wi-Fi, Zigbee, and then I discussed MQTT, I discussed COPE, then there's DDS, NFC. NFC is the protocol that you will find that is used in smart payments using mobile phones. So now you can also make payments using mobile phones. You just have to tap your phone against a terminal and you have made the payment. Okay, so then there are cellular mobile protocols, because in the IoT scenario your mobile phone can also be connected to devices. Okay, or as I showed, your mobile phone can be a subscriber. Okay, then there is AMQP, LoRaWAN. There is RFID, with which some of you might be familiar, like RFID tags or RFID cards are used for marking attendance at a place or for getting entry to a building or a facility. Then there's Z-Wave, Sigfox, IoT Threads in Ocean. So there are a number of these protocols. They have different features. Some have high bandwidth, some have low bandwidth. So they all have their purpose. Okay. For instance, Bluetooth gives you a small range connectivity. So two mobile phones can talk to each other using Bluetooth also. But as your range increases, as the distance between them increases, you need something bigger. Maybe you need Wi-Fi. Okay. So these are the reasons why you have so many different kinds of devices. So I will come to all those questions at the end. Let me just go through this first. Okay. Now, scope of IoT. So what is the scope? So IoT has a very broad scope, and as it was mentioned in session 1, there is scope for home and building automation. I gave you one example, Lightify, the smart bulb. There is scope in agriculture, for which I will show you a video. There is a scope in asset tracking. So Amazon dash button is a very good example of asset tracking, because by using that button, you are able to track whether you're running short of your beverages or your detergent or whatever it is. Then IoT has applications in medical. So devices like Fitbit or smartwatches that some of you may be using, that is essentially an IoT device. Okay. Then it has application in smart city. So I gave an example of smart electricity distribution using smart meters. So that is one example related to smart cities. Okay. So let me show you this video. This is a case study of connecting smart farms with Vodafone IoT. So this was done by Vodafone IoT in Australia. Okay, so let's watch this video first. Are you able to, were you able to hear the sound of the video? Okay. Okay, so as you saw in that video, that farm was around 70,000 acres of size, and it houses around 7,000 animals. Now, managing a property like this, of course, in India, we don't have such big farms. Whether for agriculture, I don't think there is any single farmer who owns maybe 20, 30,000 acres of land, or somebody who is rearing sheep or cattle for meat production. But when you have this scale of operations, it's very difficult to monitor the quality of soil, the quality of biomass, the amount of water that is available to your animals as they graze around, and how do you monitor the movement of animals itself. So if you could connect all of these components together using different kinds of sensors, then your management and operation of your farm can become much easier. And also with this collection of sensors and the data that they collect, you will have a large volume of data that you can analyze over a period of time to understand how your farm has evolved over the years or over months in terms of utilization of the resources that are there on the farm by the animals, by the cattle. So this is very interesting, and it is these kind of things which make IoT much more interesting and challenging for people who are really keen on seeing how IoT can be used. Turning on a bulb or a fan by clicking a button on your laptop, for you and I, that may not be very significant, but for somebody who has movement problems, so let's say there is a member in the house, in somebody's house, who can't walk around easily, who has trouble walking around. How do such people get better control of their lives? So they can turn on a light or a fan in their room by tapping on their phone. They don't have to go and reach out to a plug point or to a switch on a board to make it all work. So it also enables those people. So it is these kind of ideas that drives innovation in Internet of Things, as well as adoption and services that different companies bring when we talk about Internet of Things. Okay. So we'll discuss that again in the Q&A section. Let's move to the challenges in the Internet of Things. So the 5 C's of Internet of Things are connectivity. Now what would happen is when you have dense device deployments, it will strain your network resources, affecting connectivity. And you are all familiar with this thing, I guess. You all have Wi-Fi at your home. How many devices do you think you can connect? And each of those connected devices will get reliable connectivity. Not many. You can't connect 10, 20, 30 devices to the Wi-Fi at home. At the most, maybe 4 or 5. So that all the users get a good experience. So this is a challenge. When very large number of devices are connected in a network, then performance of the network is going to get strained because the resources that the network has is only limited. So how do you deal with such cases? Then continuity. Now a lot of IoT devices operate using batteries. So how do you ensure that those devices have a longer operating life period before you have to change the battery? Okay. So that is why we have some low power protocols like LoRa, Sigfox, which do not consume much power. So the sensors or the IoT devices communicate using these low power protocols, which don't consume a high amount of energy, thus extending the battery life of your device. As well as your device can have low power operating modes. So some of these microcontrollers and microprocessors, they can operate in low power mode. Okay. One example, not from an IoT, but from your general life that you all would have observed is your laptop. On your laptop, if you're using a Windows or Linux, your screen would turn off after a point if there's no activity. Why is that done? That is done to put your laptop into low power operating mode so that it conserves power. Okay, it conserves the battery life, the life of the battery on your laptop. So these are the reasons. So this is how low power operations or low power protocols help in extending the continuity of a device. Then we have compliance. So all IoT devices must comply to radio standards and regulatory requirements. And why is that? Because most IoT devices will be transmitting some radio frequency signal, okay, or receiving some radio frequency signal. So especially devices which transmit radio frequency signals, they have to adhere to radio standards and regulatory requirements like EMC and SAR test. So EMC is your electromagnetic compatibility test, and SAR is a specific absorption rate, which refers to how much radio frequency energy or EM energy can people be exposed to. And if you take your phone, okay, if you look at the back side of your phone, you will, or somewhere in your phone also you can see, because your phone is a transmitter, you can see what is the EMC threshold, or there is an EMC rating, or there is an EMC test passed, or something like that mentioned. Okay. Then coexistence. So the radio channel, which is used to communicate, which is used by two devices to communicate with each other, that can suffer from congestion. If you have millions of devices, think of the radio channel as a road, okay, or as a highway. So what happens when you put thousands of cars and motorbikes on the road? There is congestion. There is not enough space for every vehicle to move faster, right? And this is what we observe in all our big cities in the country. It's the same concept with radio channels. Radio channels, if hundreds, thousands, millions of devices are using the radio channel, there will be congestion in the radio channel. So the speed with which the packets will be transmitted in the radio channel will be will have a negative effect. Then we have cybersecurity, and I think one of the questions that was asked in the chat window is related to this. So I will answer this again later once we finish the presentation. But here in cybersecurity is also an important point in IoT, because your edge devices, they may need to be updated. So how will you update the edge devices? And your edge devices may not be physically accessible to you all the time. If you have thousands of sensors, like on that farm, if you have deployed say 1000 sensors and you have to update the firmware or the software in that IoT device, you can't go manually update it on each and every sensor. So you will be using over the air methods, like the way your phone software gets updated. So when the firmware or the software on your phone has to be updated, you observe your phone will prompt you software update available. How is that happening? That is happening through an over-the-air transfer mechanism. The company is pushing, the update over the air. So that's essentially, in communication mechanism, and then you have to install it. But these expose your devices to vulnerabilities, to security vulnerabilities. So how does one deal with those things? Okay. So one of the protocols that is given here, IoT threads. Okay. So IoT threads is one protocol which looks at security in IoT, especially for cases where your devices have to be really secure in an IoT deployment scenario. Then we also have system level development challenges. So operating system considerations, what kind of OS will you run? If you have to run an OS on an IoT device, you can't run Windows 10. There's no way that can be run. Okay. So Ubuntu, which is a Linux distribution, it has something called Ubuntu IoT. Okay. This is for IoT devices. Okay. That doesn't mean it is for edge devices. It may be for gateways and routers and so on and so forth, or for those IoT devices which have some compute capability in them. Okay. Then selection of gateways, whether you will use Bluetooth gateway, whether you will use Wi-Fi or Zigbee, what will you use for your IoT design case? And then the choice of IoT platform, build or buy. Now, these days, a number of platforms are available in the market. I'm quite sure that all of you are familiar with terms like Raspberry Pi or Arduino. And a lot of people use Raspberry Pi or Arduino to build small IoT projects. So you are essentially buying those platforms and building your IoT solution. But then the question is, do you also want to build your IoT platform itself completely, which means instead of using Raspberry Pi or Arduino, do you want to build your own version of Raspberry Pi or your own version of Arduino? So that is this choice is essentially a business choice, because this has connections with the money that need to be spent. So it has a financial implication. Okay. Then testing. Now, because you have a large number of distributed nodes in your system, how would you test them? Okay. So testing of such a system, which is distributed in nature, becomes challenging. Okay. Ensuring that each and every sensor is working, ensuring that each and every connection between the sensor and the, let's say, the central controller is working. Then security of devices. So variety of devices and protocols are available. And essentially, if you see an IoT system is a heterogeneous system. So you have different kinds of devices, you have different kinds of protocols. So how will you ensure that they are all secure together? Because in security, there is a common saying that your security is only as strong as the weakest link in your system. So if you break one link, if somebody breaks one link, they are able to log into your system. And there are plenty of such examples. You would have read about people breaking into somebody's, smart refrigerator, smart TV, because the router, the internet router that they had not changed the default password. Okay, and if you search on the internet, you will find quite a number of websites that maintain a list of default user IDs and default passwords of thousands of routers and such network devices. And if you do a little bit of learning on network security, you will be able to penetrate those devices. So this makes your system security very challenging. And then user-centric design, which is that your IoT system should be easy to use. So take for example your smartwatch or Fitbit, or these fitness bands that these days people wear on their wrist or on, when they go for jogging and for exercises. It is so easy for you to use it, right? You just have to tap and it begins to function. You just have to do a few more interactions with the device, and your device will start communicating your data to your smartphone or to your cloud account. So the design has to be user-centric, okay? In the case where it's a personal IoT device. In case of industrial IoT, like say the electricity distribution that I discussed earlier, you don't really have to focus on user like you would have to do in case of a personal IoT device like Fitbit. Okay. But this is still a challenge in IoT system development. Okay, so that was a broad, I would not say a very broad, but somewhat focused overview of Internet of Things, its architecture, protocol, devices, and challenges. Next, I will talk about a very specific challenge, which is analytics in the Internet of Things. And I will specifically talk about machine learning on IoT devices. I'm quite sure that a lot of you are interested in machine learning, at least you read about it, you hear about it. So I'll just focus on this one single challenge in this talk after the overview that I have given. So machine learning or deep learning is primarily based on neural network architectures. Okay, a neural network is based on the concept of perceptron. So this, what you see here, is a perceptron. Okay, a model of the neuron in human brain. Okay, here x1, x2 to xm are the inputs. Okay, and w1, w2, wm are the weights. B is bias, which always takes a value of 1. So the inputs are multiplied with the weights, they are summed together, and then there is a activation function applied to get the output y. Okay, so if you write it mathematically, it will look something like this: y output equals a times b plus sum of xi and yi over all I. Okay, so xi and yi is a linear combination of inputs because we are simply multiplying x with w and adding it all up. So it's called a linear combination of inputs. B is the bias value that is added, and over this value we apply a non-linear activation function which constrains the output y in the range 0 to 1. Okay, and why we want it to be constrained in the range 0 to 1? Because the probability value, if you remember from probability, the probability of any event is always in the range of 0 to 1. Okay, so all your classification task, recognition task can be treated as some sort of a probability that, say, this particular digit is 6 or this particular digit is 5. What is the probability that this particular digit shown in an image is 6? Okay, that is why we apply nonlinear activation function. And if you look at the history of this development, machine learning or deep learning concepts were proposed in early 1960s also. Okay, but they could not take off at that time because at that time there was not so much compute power as we have today, and this linear combination of inputs, at that time there was no nonlinear activation function. So using the linear combination of inputs, you cannot solve problems which are nonlinear in nature. Okay, for instance, if you have to create a neural network that behaves like an XOR gate, okay, it is not possible to create such a network unless you have a non-linear activation function also available. Okay. Now think of this x and w as, very high number of x's and very high number of w's. So your m is a very high in value. That is the case today. Okay. So tools of the trade, what are the tools that are used in machine learning, deep learning? Massive compute hardware. Okay. So GPUs, so this is a Titan RTX GPU from NVIDIA, multi-core processors. They provide tremendous compute capability. Massive data sets. Okay. So data sets like ImageNet, which has millions of images, again, open image data set V6, it also has thousands of images. You have massive data sets available, and you can store all of them because storage has now become cheaper. Okay. And then you have enabling software frameworks like TensorFlow, Keras, which help you in training a neural network model easily without even having to understand the mathematics behind it. So for TensorFlow, there is something called TensorFlow Lite, which is used for deployment of machine learning models on IoT devices, on phones, basically smaller devices, not on GPUs. Okay. Now, earlier in 1960s, 1970s, when AI was first being discussed, okay, we did not have GPUs. We did not have such massive data sets. And the storage also was not cheaper. Okay. So that was also one reason why AI MLDL techniques did not progress much in 1960s, 70s. There are a few other reasons, but this was also one reason. Today, because we have so much compute power, we can collect so much data, then we can also train so much easily the models. So this model needs to be trained. Okay, that is how you get the values of W1, W2, Wm. Now training needs a lot of data. Okay, so principally, if you look at today's machine learning, deep learning methods, they are based on supervised learning approach, which means that there is labeled data set available, which is used to train the model. And for that, you need massive data sets. In the early days, 60s, 70s, that was not the case. So AI was not progressing much. But now we have so much of compute power and easier storage of so much of data that we can train the model easily and deploy it. Okay. Now, let's go back a bit to this equation. So here xi yi is dot product, and it can be written as x transpose w by treating x and w as matrices. Okay. Now think of x and w as being very big matrices. And then remember what I told you, that on your edge devices, you don't have much compute power. You don't have much on-chip storage. Where will you store the weight? In typical MLDL deployments, this is stored off-chip, okay, in external DDR memory, or if on-chip you have some megabytes of memory, then there. But on your IoT devices, you don't have so much of on-chip memory, and then it's not so much connected to the DDR devices also. So there is a problem. It's not so easy to deploy these machine learning models on IoT devices. So that's a real challenge. Okay. Another example here. Look at this common activation function. Here we have the sigmoid function that constrains any x in the range 0 to 1. Okay. For every y, you have to do this, apply this activation function. Okay. So computing this becomes a very compute expensive process. Okay, this is not a simple computation as 1 + 1 = 2. Okay. Another example of activation function is ReLU function, where whatever you give as input, it is bound in the range 0 to x. Okay. So while this is a rather simpler function, rectified linear unit, the sigmoid functions are not so easy because this computation takes more resources. This presents a challenge when you want to deploy machine learning, deep learning models on IoT devices. Let's take a look at deep neural network. So this is LeNet 5. This is a convolutional neural network for digit recognition, where this is your input image. Okay, here it's a character, it's a letter A. You can have it a digit also, 4, 5, whatever you want. It is given as input to a convolutional layer, which creates feature maps. Then some subsampling is done, then again convolution is done, again subsampling is done, again fully connected layers are there, and there are some other kinds of layers, and you get your output. It is not so important to understand what these layers are and what they actually do. What is important to understand from an IoT point of view is that at every layer you are generating huge amount of data. So these feature maps, you can see 8 by 20, 6 feature maps. So So at every level, a lot of data is being generated, and all of that data typically is sent to external memory, then brought back for computation as and when needed, and then sent again. That is where GPUs excel, because if you take a GPU card, it has a lot of memory on it, and GPU itself is a very powerful processor architecture. On the other hand, for IoT systems, that's not the case. Your IoT is a very simple device. Okay. So if you look at the computational requirements of these models, like the one that I showed to you, LeNet, this is the input size, okay, 28 by 28 pixels. Input is an image, okay, and look at the number of weights that is there. LeNet has 431,000 weights, 431,000 weights, okay, if LeNet is configured on the MNIST dataset, which is a digit recognition dataset. Look at the other networks. For the other networks which are for image recognition or some image related task, look at the number of weights. It's in millions, 61 million, 138 million, so on and so forth. Now, take the example of LeNet itself, 431,000 weights. If each weight was just 1 bit, let's assume. So how many bits you need? You need 431,000 bits. Okay, that is roughly 431 kilobyte of storage needed. And we saw that your Amazon Echo Dot has only 256 kilobyte of storage, the ARM processor there on chip. So you can't even fit this simple model on the ARM processor that is there in your Echo Dot. So now I hope you can appreciate that there's so much of, because of these huge amount of weight, there's so much of a challenge in implementing these models on IoT devices. And if you take 8-bit representation or floating point representation of these weight values, then your memory requirement increases much more. So this is a graph that shows you parameters versus maximum GPU memory utilization, and there are different kinds of neural networks shown here. So here it is mobile net, VGG net, etc. and sorry, not VGG, mobile net, dense net, Google net, squeeze net. So some of these are models related to resource constrained devices, okay, whereas here VGG, etc. at the top you can see, and the size of parameters is in megabytes, 600 megabytes, 500 megabytes, and the memory utilization is also in megabytes. Maximum memory GPU utilization is 1600 megabytes, 1400 megabytes. So this is huge amount of memory which is not there on your IoT devices, okay, at least not on typical IoT devices. So what can be done? So there are three important concepts in CNN or DNN, which are weight, feature maps, and inputs, and they're all numbers. And number can be represented in single precision floating point 32 bits, double precision 64 bits, or integers. Okay, so clearly the choice of number representation affects the memory requirements. So the number representation affects the hardware requirements for computation, because floating point multipliers would be needed if you are doing floating point multiplication. So here your storage, how much memory you need, will be affected by whether you're using 32 bits for every number or 64 bits or 8 bits. But there is also another difference, which is the computation that you do on integers and the computation that you do on floating point numbers. The in computer arithmetic, they're not exactly same. Okay, so if you are adding two floating point numbers, it is not as simple as adding two integers. Okay, typically one would expect to have floating point units in the processor. So for instance, for floating point multiplication, you should have floating point multiplier. For floating point addition, you should have floating point adder. If that is not the case, then perhaps you have to go back to using integers. So this restriction or this need also affects the choice of hardware for CNN or DNN implementation. Not all processors come with floating point units. This also affects memory read-write bandwidth and latency, because if you're using, say, 64 bits to represent the data, then the amount of data that you have to read from memory also increases. So your read-write bandwidth will be higher, and latency could also be higher because you're reading more data. This also affects power dissipation, because if you transmit or if you transfer, say, as an example, 100 words of 64 bytes each from memory, and you compare that with, say, transferring 100 words of 1 byte each from memory, the power dissipated during the transmission will be lower in the second case. So your number representation is having an impact on the memory, on the kind of hardware you can choose, on the memory bandwidth and latency, and on the power dissipation. So this slide shows you the cost of data movement, okay? Where if you take ALU as the base, then to access a value from the register file in your processor and bring it to ALU, the cost is almost the same in terms of energy. But if you have processing elements, okay, in your network architecture, in your neural network, where these are processing the input data, then when you bring the value from P's to ALU, it takes almost twice the energy. If you're bringing a data from a buffer to an ALU, it is almost 6 times the base energy cost. And when you're bringing the data from DRAM to the ALU, it is almost 200 times. Okay, so DRAM is your external memory. So you can see that this increase in energy is also exponential, depending on how far the data is from your main ALU, where your arithmetic and logical operations happen. So if it is in RF register file, it is almost the same cost, but if it is in DRAM, it's almost 200 times. Okay. And then if you look at the sigmoid function, if you want to calculate the sigmoid function 1 over 1 plus e raised to minus x, this calculation will be expensive when you have hundreds of neurons in the output layer, where you are applying this function on output y. So if you look at this itself, what operations it has? It has 1 over e raised to x to find out e raised to minus x, then x multiplications to calculate the value e raised to x, and one final division. So just for one output of x, you have to do these 3 tasks, and division is also an expensive process. And if all of this is in floating point, it becomes even more expensive. So these all affect whether you can use an IoT device or not, or what kind of IoT device you can use to implement MLDL models. Okay. So in summary, the computational requirements are high amount of memory for storage of weights and feature maps, high bandwidth memory for fast data movement, computational resources for floating point arithmetic like multiply, divide, add, and GPUs excel at this, and hence it is GPUs which are generally used for training and inference. But now with the IoT, we want to have intelligence at the edge. And one way to have intelligence is to use AI techniques, MLDL techniques. So that is why there is a growing interest in the deployment of AI methods or MLDL models on IoT devices. So for IoT devices, if you look at their characteristics, they have processor with less compute power, less on-chip memory, battery operated, less operating clock frequency. So essentially these are resource constrained devices. So the question is, how will we do machine learning on IoT devices? So we have two main phases in CNN or DNN: training, which takes a lot of time and consumes a lot of power, and inference. So run training on GPUs or in cloud servers and then deploy trained model for inference on the devices. So training cannot be done on IoT devices, at least not so far. Though if you read research literature, people are trying to come up with methods to do training also on the device. Okay. So train on GPUs or in cloud servers. Once your model is ready, it has been trained, then you deploy that model on the devices. Or you can also send tasks for CNN or DNN to cloud server from IoT device. So one example of this is your Amazon Echo Dot. There your voice recognition, your speech recognition happens on the cloud server. So Amazon through the Alexa app, Echo Dot through the Alexa app sends your voice commands to a cloud server where it is analyzed. So say if you have said call XYZ, so call XYZ, this is understood, this speech recognition is done in the cloud server, and then from there a command is pushed to your Amazon Echo Dot to make a call to XYZ contact in the contact list. Okay, so in this case the task for CNN or DNN has been pushed to the cloud server. So the deployment models, I am giving you two examples. Amazon Echo Dot, no on-device inference and needs network connectivity. So I just explained how this works. The other one is Intel Neural Compute Stick, where we have on-device inference but needs no network connectivity. So in this case, what is done is that you train your model and then you deploy your model on this compute stick. And this is a USB compute stick. So you can plug it to the USB port of say Raspberry Pi or similar other devices. And then through using some software that Intel provides, you can make this, the model that is here, that can be used on the Raspberry Pi, for example, to do some tasks. So now you are doing on-device inference without any network connectivity. Okay, so these are the two main models of deploying MLDL on IoT devices. Now, how does on-device inference work? So essentially, what we have to do is we have to make the model smaller. Okay, otherwise we can't deploy on IoT devices. So how do we make the model smaller? Network pruning, quantization, and choosing an improved number representation. These are the three methods, three main methods. Of course, the first, these are the three main methods, the other methods also, but I'll just briefly touch upon these three. So network pruning says if you have this network before pruning, then you remove some connections, remove some neurons, you get a simplified network. So clearly this network has less storage requirements, less compute requirements. By following this approach, it has been shown in research that the number of parameters can be reduced by 9x and 13x for AlexNet and the VCG16 models. So then after that, this model perhaps will become small enough to deploy on an IoT device. Then quantization. So quantization, I guess most of you will be familiar with. It is a familiar topic from signal processing, where weight values are quantized. So here, this is the red is your analog signal, and then you chop it into chunks, and any analog signal in this range will have a value of 101 or 110 depending on what you choose, right? So here any analog signal in this range will have a value of this or this depending on what you choose. So now you don't have to store so many different analog values. You can simply use one value to represent this set of analog values. So your storage requirements, so you can think of your weights as analog signals. You can quantize the weights. So now you don't have to store that many weights. You have to store less number of weights. So your storage becomes less. the requirements become smaller, your model becomes smaller. Okay, so here is one result. This is using TensorFlow Lite. You can go and look up TensorFlow Lite. There are different types of quantization. So this is post-training quantization, post-training dynamic range quantization, post-training integer quantization, and quantization-aware training. So for each of these techniques, some results are given here, like what is the reduction in size. So 50%, 75%, so on and so forth, and what are the supported hardware. So these hardware are supported by TensorFlow Lite. The link you can see at the bottom, or if you just search in Google TensorFlow Lite, you will find this. So you can see by using quantization, you are able to reduce the size of the model, which is a good thing, because now you can perhaps deploy it on the IoT device. Here is the effect of quantization. So here we have we see some models here. These models. So these are actually models developed for mobile devices. Okay, so they are smaller in size compared to GPUs, but they are still not so small that you can deploy them on an IoT devices. But they are smaller, and here it shows that if you do some this table shows that if you do some quantization related optimization on these models, this is how the latencies and other parameters change. So take the first example, MobileNet 224. The original latency is 112. After post-training quantization, it comes to original is 124. Post-training quantization is 112, and then quantization aware training 64. So it becomes almost half. Original size is 16.9 MB. After that, it is 4.3 MB. It becomes almost 1/4. So by applying these methods, you can reduce the size of the model, and that also can result in reduction in the latency of the model. Yeah. Then the third one is number representation, bfloat16, which is a very recently proposed number representation. This is from Google. That is why it is called Brain Floating Point, because it comes from Google's Google Brain project. So instead of using a 32-bit floating point number, this is a 16-bit floating point number with a floating radix. Okay. What is the difference? Let's look at this table here. This table is more important. Your float 32 has 32 bits, uses 8-bit exponent and 23 bits of fraction. That is your standard IEEE single precision floating point number. So its precision is high because of 23 bits of fraction, and its range is also high because it makes use of 8 bits of exponent. Float 16 is just half of this. It uses 16 bits, 5 bits of exponent and 10 bits of fraction. 1 bit is for sign bit. Same is in float 32. There is 1 bit which is for sign bit. Now its precision is low because from 23 it came to 10, and its range is also low because the exponent is 5, from 8 to 5. But it is faster because it's a smaller number, so you can compute faster with this. bfloat16, what it tries to do is it tries to preserve the range. We need a higher dynamic range. So range is based on exponents. So it keeps 8 exponents, but sacrifices precision. So precision becomes lower because it uses only 7 bits. And why was this design done? What is the motivation? The motivation is that in many CNN, DNN applications, the precision is not that important. Like in image recognition tasks, even if say the picture of the cat is not very accurate, you can still figure out that it's a cat, right? If you take your video streams, when you watch a video, even if say it's little blurred, okay, not very clear, you can still figure out who the actors are and what is going on, so on and so forth. So there are many applications which tolerate some loss of precision. Okay, so for such applications, we want to tolerate loss of precision, but we want to have the dynamic range available, the full dynamic range. So that is why bfloat16 was proposed. And then we have reduced order models or smaller models. Examples are MobileNet, SqueezeNet, YOLO. So these are models which you build from scratch and you focus on size and speed. Okay, so you don't take a a pre-trained model and then you quantize it and then do something, but you try to come up with a smaller model itself. So MobileNet, SqueezeNet, YOLO, these are examples of such models. So this is MobileNet, okay, which uses the concept of depth-wise separable convolution. You don't have to worry about the details of this, but this is something related to signal processing. So standard convolution is so many operations. In depth-wise convolution, these filters are broken down into dk times dk and times m, and then finally we apply a one by one convolution on m times n to get the result. So by linearly separating the convolution filters, you are able to speed up the performance and have less storage requirements. So this is a slide that shows performance parameters for on-device inference, power versus latency. What is important to see here is that for the same type of or same number of operations, you can have different latencies. Okay, look at this one here. MAC is multiply accumulate operations, so million max. So here for 50 million max, you can have different kinds of latencies. So, and here for the same latency, you can have different number of millions of MAC operations in your model. So so what it shows is that the number of MAC operations is not really is not really a measure of latency. When you learn about in some more detail about on-device inference, you will see that people might often say that the number of MAC operations is a measure of how complex the model is and how much latency it will have. But this graph here shows that it's not like that. Okay, so this is an important research result. Now there are these software frameworks for ML with IoT models. I won't get into these. You can look them up. These are all open source. The ones that I have listed here, these are all open source software frameworks where you can try to implement a machine learning model on IoT device. So TensorFlow Lite, etc., are here, and from many different companies. Okay. So in conclusion, is on-device inference a solved problem? The answer is no. And where you should focus to improve on-device performance? So you should, if you're doing research in this area, you want to know more in this area. Mathematics of computation, as I showed you, floating point numbers, then floating point arithmetic, that is where you can focus. Architecture, the architecture of the model itself you can focus, because one could actually come up with simpler architectures which these MobileNet, SqueezeNet, etc. models demonstrate. And the last one is hardware level optimizations. So you can do some optimization on computation and memory, the way these computation is done, the way memory is accessed. So with that, I will end this presentation and I will take the questions. Let's take one by one. So one is whether float 16 is one is whether float 16 is required or fixed is enough. So float 16 is required, fixed is not enough, because in certain applications you need a high dynamic range and precision also. If you are working with fixed point format, in fixed point format, the position of your decimal point is fixed. In floating point, it can float. So depending on your application's need, your fixed point format may not be enough. So it depends on your application. Next question is, what about my thoughts on dynamic floating points? So floating point number representation is actually a dynamic floating point number representation. Okay, because with 23 bits of fraction, you can in the decimal number representation, the number of digits that you can have as fraction can be much more. Dynamic approximate computing, yes, you can do dynamic approximate computing. In fact, this concept of applications that can tolerate some loss in precision, that is essentially approximate computing. It's not exact. Quantization as a concept is also not exact, it's approximation, right? One range of values is being approximated to one single value. So all of these methods can be used for deploying MLDL models on IoT. Any other question? So Aditya had one question. I think he had raised his hand. So Mr. Aditya Nalwaya, do you still have your question? Okay, so if there are no more questions, then we will end this session. Okay, what are the research areas? So the research areas, you see, if you talk about, say, machine learning, deep learning on IoT, so that's one research area. If you want to work on IoT protocols, then that's another research area. How can you come up with, say, a new protocol that consumes less energy? Okay, or new protocol that helps connect devices in constrained settings. Okay, then then another research area is the application of these protocols. So as I showed you, when you scale the number of deployments, when you scale the number of sensors and actuators, then how would you test that they are all working very properly? So testing is a challenge. Okay, then you have to updates. If you remember the slide where I showed you 5 C's and then the challenges after that, so those are the principal challenges in IoT. Okay, IoT in itself. If you add things like analytics in IoT or machine learning in IoT, then that becomes your next additional research areas. So I will send these slides also by email, and then later on I will upload the videos. Today's videos will be uploaded by end of tomorrow on YouTube. So I will share all of that through email. Okay. So any other question? Okay, so if no other question, then we will stop here and we will take a break for lunch. It has been a long day for all of you. So because of the cyber physical systems is actually cyber physical systems is not much different from IoT. It is just that cyber physical system makes use of IoT. It's another term where you connect cyber, basically your internet and networks, and you connect physical devices. In CPS, we talk of more abstract, in a more abstract way. So your smart electric meter, okay, not meter, sorry, a smart electricity distribution system. That is a cyber physical system. But inside of it, if you look at if you go into the details, you will see it's making use of sensors, actuators, smart meters. So that is where we talk about IoT. So IoT is you can say the base over which your CPS systems are built. Okay. So next session will start at 2:30. There is no separate attendance for every session. The attendance is for the day, just as we do it in a real face-to-face FDP. Okay, so if you have marked your attendance once, you don't need to mark it again. Okay, so next session will start at 2:30. We will have a speaker from Indian Institute of Technology, Palakkad, and he will talk about some IoT processor architecture and those things. Okay, so I have already sent you the link for the third session. Please use that link to join at 2:30. So thank you all. It was a face-to-face session. I would have arranged lunch for you, but this is This is virtual. So we'll meet up at 2:30. If anybody has attendance problem at that time, we will solve it. Yes, Anjali, what is your question? So Anjali has raised a hand. You can ask your question. Okay, so we'll meet at 2:30. Take care, everyone. Bye bye.